today's topic is magnetic field calculation due to loop or circular coil. Using again the Biot-Savart law. So initially we will calculate this magnetic field using the Biot-Savart law. Similar is the case that we have done already in the electrostatics. Electrostatics আমরা কি করি? Electrostatics first of all we calculate the electric field using the Coulomb's law. Then we derive the same electric field formula using the Gauss law. Here also we follow the same sequence. Initially we will use the Biot-Savart law to calculate the magnetic field lines or magnetic field vectors, and finally once we complete the Biot-Savart law, then we go for the another law that is called the Ampere's law, similar to the Gauss law. So using this Biot-Savart law, initially I want to calculate the magnetic field due to a loop. So what is loop? Loop must be a closed diagram. So loop must be a closed diagram. So we will discuss about the loop which is of circular coil. Circular coil means cross-sectional circular. So loop can be of any cross-section. It may be a square cross-section, it may be rectangular cross-section, it may be triangular cross-section. So depending on the geometry of the coil, the name of the coil will be changed. But whenever I am saying loop, it must be a closed. It cannot be open. So through a closed coil, if the current is being flowing, so my intention is to check how much amount of magnetic field is being produced. So for that, first of all, I have to calculate the direction. So let us say along a loop, the current is being flowing in this direction. So this is the direction in which the current is being flowing. So you have to curl the fingers of right hand along the direction of the current, and your thumb will give the direction of magnetic field. So if I curl my right hand finger along this I direction of current flow, so my thumb will be pointed upward. So upward is the direction of the magnetic field. And at center of the loop, if I consider the center of the loop, it should be a simply vertical line. But if I move away from the center, the lines will be curved one. So if I draw a vertical line facing upward, that means the tendency of this loop is to behave as a magnet. Why? Because if I replace this by a permanent magnet, so this kind of loop can be treated as a magnet whose north pole is facing upward. Why? Because we know that from the north pole the magnetic field lines are coming out. So from the north pole the magnetic field lines are coming out, and in this situation also this loop is acting as a simple bar magnet whose north pole is facing upward, since the current is being flowing in the clockwise direction from the top. If I reverse the current direction, so if I say I reverse this current direction along this direction, so if I fold my fingers along this direction, so thumb will be pointed now downwards. So downward is the direction of the magnetic field corresponding to the center. If I move away from the center line, so then the field line will be bent. It will not be a straight line, so it will be a curved line. But I am bothered about this field line which is passing to the center. So for that, it appears to be a line which is vertically downward. So this particular loop can be replaced by another bar magnet whose north pole is now facing downward. So that means from this north pole, since the magnetic field lines are coming down, so I can say this is acting as the north pole which is facing downward. Why this similarity is important? Because if I place two different loops, let us say I place one loop over here, another loop below of this. So from this loop, let us say if the current is being flowing in this direction, and for the bottommost loop, let the current is flowing in the other direction. So now these two loops, so first loop is behaving as a magnet whose north pole is facing upward. That means south pole is the facing downward. Why? Because the magnetic field line is upward. Okay. So for the bottom loop, the magnetic field line is downward. That means for this loop, so this can be treated as another magnet whose north pole is downward and south pole is upward. So now these two magnets coming south pole together. These two magnets are coming to south pole together. So they will repel each other. So they will repel each other means actually the magnets are not there. Actually the loops are there. So I can do the similarity analysis and I can say if these two type of loops are there, in which the current are being flowing in the opposite direction, so I can conclude that these two loops will now repel each other. Okay, similarly if I give the current direction the same direction, so now the north pole and south pole come together, so ultimately they will attract. So this analogy will basically give us to replace the entire loop by a magnet. So for that, every time you have to check the direction, and for direction you have to follow the right hand thumb. So fingers of right hand are to be curled in the direction of the current. So current may be either clockwise or anti-clockwise in a particular loop. And the stretched thumb is in the direction of the magnetic. So when I stretch my thumb along the direction of the magnetic field, so direction of the thumb will give the B vector direction. And for any type of loop, this is valid for any loop. So if I say this is a, let us say there is a coil placed in the horizontal plane, like this is a circular square coil. So through this, if I say this is the direction of the current flowing, so can I say now the magnetic field line which is passing through the center of this coil is projected vertically upward. Okay, so why? Because I am only drawing the vertical line at the center of the loop, because that will give the idea that all the other field lines are not vertical, it should be somewhat curved. But that will give the idea that now this coil is behaving as a coil in which the magnetic field lines is upward. Okay, so if I change the direction, so then the direction of the magnetic field will be changed. So by this method, I have to first calculate the direction in which the magnetic field lines are going. Okay, so but actually what happens, similar to the electric field lines, magnetic field lines are also not visible. Okay, magnetic field lines are also not visible, but these can be visualized only when I sprinkle some kind of iron dust over here, and if I follow the pattern of the iron dust, then I can see that if I say this is a loop, which the current is being flowing in this direction, I. So if I mark this point as point A and that point as point B, can I say that through the point A, current appears to go inside the plane of paper if I mark at cross. So similarly, through the point B, the current is moving out of the plane, so it is marked to dot. So if I mark the point A as cross, that means I assume that the current is being going inside the plane of paper. And from point B, the current is coming out. So if I find that current is going into the plane of paper, so for that situation, I have to put my thumb, not the finger. Now put your thumb along this cross direction, that is into the plane of paper, and if I curl my finger of right hand, so then the curl lines will be like this way. So these are basically the direction of curling, and along that if I put the arrows, so this will give the direction of the magnetic field lines about this point A. Similarly, for the point B, since my current is coming out of the plane, so now I have to place my thumb towards my face. So if I feel that if I curl my finger, so then the direction of the magnetic field line should be in the opposite direction. So these are the basically the magnetic field lines, and these magnetic field lines, once we learn about the property of the magnetic field line, then we ensure that these lines are closed lines. These lines are bound to be closed lines. So this is the difference between the electric field and the magnetic field line. So in magnetic field lines, every line must be closed one. But this loop cannot intersect with the other loop. Okay. So for the right hand part, for the A part, there are certain kind of loops. For the B part, there is another kind of loop. But these two loops cannot intersect with each other. That means at the point, at the middle point of the coil, that means at the center point of the coil, there is only one single line which is vertically upward. Why? Because I am saying the current direction is toward that direction. Okay. So like this, you have to plot it. Like this, you have to plot it. And in order to plot or in order to visualize it, you have to sprinkle some kind of iron dust. Once I sprinkle some kind of iron dust, all the iron particles will be aligned along the direction of the magnetic field. But this arrow direction has to be obtained. Arrow directions have to be obtained by placing a compass. So once I place a magnetic needle about the point A, and if I move the needle, so every time the arrow will be pointed along the arrow direction. With the pointer of the compass, North Pole, will be always along this direction. So once I follow the compass needle, then I can plot this kind of arrows or this kind of diagram. So basically, this diagram helps us to ensure that there is a certain kind of magnetic field will be generated because of the current carrying coil or current carrying. Okay, and once I got an idea of a loop, so every time I can analyze this loop by a simple bar magnet. So for this kind of loop, as I said, that since the I is flowing in this direction, so this kind of loop is behaving as a bar magnet facing, it is analogous to a bar magnet facing north pole upward and south pole downward. Why? Because for all the thing, north pole is basically the pole from where the magnetic field lines are coming out. Okay. So this is the analogy that every time you draw so that you can eliminate the loop by a simple bar. Okay. Now the question comes, what is the value of magnetic? Because I know what is the direction, how to calculate the direction for any kind of loop. Now the question comes up, I want to calculate the magnetic field on the axis of a circular. So there is a circular coil. So let us say O is the center. I want to calculate the magnetic field at point P, which is at a distance of x from the O point. Okay, so P is the point which is outside the coil. And through this coil, let us say I amount of current is being flowing. And along the I direction, you have to assume the DL. Okay, so if I say this is the elemental current length, DL, so that DL is along the I direction. So every time you have to ensure that the DL you are taking along the current direction. Now, the point is that once I find the current element, now this point has to be joined with the point P, where I want to calculate the magnetic field line. If I join this, then this distance is basically our R. So R is the position vector of the current element DL from where I measure the point P. Yes, R is that position vector of the point P from where? From where the current element. So from current element I am measuring this R. Let us say this R is making an angle theta with the x-axis or the OP axis or the axial plane. So if I say for this DL, so can I say DL vector is always perpendicular to R vector? So DL is the line which is drawn on the ring itself. And from this point I am drawing another line. So this angle is always 90 degrees. Okay. So DL is making an angle R, making an angle 90 degree with the R. So corresponding to the cross loop, because if I apply the Biot-Savart law, so law is basically calculation of the dB vector. So dB is how much? dB is equals to mu naught by 4 pi into DL vector cross R vector. DL vector cross R vector divided by mod of R cube, or simply R cube I can write it. Okay. Basically, so if I place the loop in a horizontal, let us say this is the plane of paper on which I draw a loop like this. Okay. So through this loop, let us say I amount of current is being flowing. So if I draw any line on this loop, so that line, let us say this is the line. So this line is measuring, the blue color line is measuring the DL vector. DL vector. Now from this axis, if you imagine this is the point P, so what is the angle I want to measure? This angle. So you can imagine that there is a loop which is on the horizontal plane, and from that point you want to mark the line joining between this DL and through the point. Every time this should be the normal to the DL vector. Every time this length should be normal to the DL vector. এটা কি বোঝা যাচ্ছে? এটা একটু নিজেকে ফিল করতে হবে। তুমি একটা মুখের সামনে একটা লুপকে ভাবার চেষ্টা কর। So from that loop you try to draw the lines. So those lines are always perpendicular to the DL. Why? Because DL is in the xy plane. Let us say if we say this is the x-axis, this is the y-axis. So DL is in the xy plane, and I want to calculate the distance which is in the z plane. That line R should always be 90 degree angle with the DL. If it is shifted, নিজে একটা ছবি আঁকার চেষ্টা কর, ছবি ভাবার চেষ্টা কর, লুপকে তারপর পয়েন্টটাকে জয়েন কর। Every point, not only this point, every point if I join, every point becomes 90 degree with this DL. With this DL, this angle is always 90. Okay, so that means DL cross R gives the value of R DL sin theta. And sin 90 is 1. So that means this number is mu naught by 4 pi. So if I apply the Biot-Savart law for this current carrying element about this point P to calculate the dB for this DL element, so that should be equal to mu naught by 4 pi into DL cross R. DL cross R value is basically R into DL into sin 90. And sin 90 is 1, so divided by R cube. So ultimately it gives mu naught by 4 pi into DL by R square. Okay, now regarding the direction, what is the direction? So you place your thumb along this DL, red arrow, and stretch the finger towards point P. Stretch the finger towards point P. So the corresponding dB vector will be perpendicular to this R line like this. What the feeling? dB vector will be perpendicular to this line. বোঝা গেল? So if we place my thumb along this DL vector and stretch the fingers of the right hand towards point P, so dB will be perpendicular to this R. Similarly, if I put another current carrying element in this direction. So let us say another DL element is there. Okay, just diagonally opposite to that. So for that, this is the R number. For that, this is the R number. And correspondingly, another dB factor can be calculated, which is again pertinent to this. Is another dB for the lower element. Okay. Now both of these dB has one component, cost component cancels out. So this vertical, so this cost component cancels out. So only you are left with this sin theta component. Okay. So what is the B vector net? dB net is along this axis. Okay, but because I have already calculated that whatever be the magnetic field direction is there for the loop should be along the axis direction for the point lying on the axis. Okay. So dB net should be, if I say this angle is theta, so ultimately dB net should be how much? dB net should be our dB cos theta, dB sin theta, dB sin, because sin theta component will be there, cos theta will be cancelled. Okay, because this angle, I am saying this angle is theta, this angle is theta. So correspondingly, this is dB. So this angle is 90 degree. So vertical component is this is 90 minus theta, this is theta. That means this component is dB cos theta. Okay. Similarly, there is another R vector. For that, this is another dB. So corresponding to the dB cos theta will be there. So both the dB cos theta will cancel out. So you are left with only dB sin theta. Okay. So net magnetic field at point P due to the small current carrying element is equals to dB sin theta. Now, whatever the value of dB that we have already calculated. So ultimately, what you can write mu naught by 4 pi into dl divided by r square into sin theta. Now, what is sin theta? For this triangle, sin theta should be equals to x by r. Okay, sin theta should be equals to capital R. So loop radius is capital R. So sin theta should be capital R by small r. So that means that should be equal to mu naught by 4 pi into 1 by r square into sin theta. Sin theta is capital R by small r into dl. Into dl. So ultimately, you have to integrate it. So once I integrate it, I am getting the value of how much? So 4 pi r square into r means 4 pi r cube. Okay. So if I integrate it, so that will be the value of total dB net. Integration of dB net will be the B at point P. That should be equal to how much? Mu naught by 4 pi. 1 r square, another r square is there. So r cube, capital R, integration of dl. Now what is the integration of dl? dl integration is total length. Total length. That is equals to 2 pi r. So ultimately we are left with this number is equals to mu naught by 4 pi capital R divided by r cube into 2 pi capital R. 2 pi capital R is the loop length. So ultimately it should be equals to 2 pi, 4 pi cancels out. So ultimately we are left with mu naught into capital R square. Sorry, another I component is there. I have missed that. So in the Bayes law there is I number. So every time the I will be the current. So current will be there. So ultimately we are left with this number multiplied by I. Okay. So small r is constant. Small r is constant. Why? Because if I fix the position of the particle or point P, so R number is fixed. So we are left with mu naught by 2 into capital I into R square into small r cube. Now what is small r? Small r is equals to how much? Small r equals to under root of r square plus x square. So if I put the small r numbers, ultimately I am getting this value. Okay. Mu naught I into r square divided by 2 times of r square plus x square whole to the power 3. So that will give the magnetic field at the point P. কোনো ডাউট আছে আপনার অব্দি? বোঝা গেছে তো? So once I calculate the magnetic field at point P, now I can do the limiting case analysis. What? That means the expression for magnetic field that we got is this. So for this situation, if I want to calculate the magnetic field at the center, at the point O, so if I place the point O, that means for this situation, at center, at O point, the value of x should be equal to 0 because x is the position of the point P measured from the center of the circle. X is the position of the particle, position of the point measured from the center of the coil. If I put x equals to 0, so ultimately what I am getting, that is equals to mu naught I into capital R square in the numerator divided by 2 times of R to the power square whole to the power 3 by 2. That is R cube. So mu naught I by 2R. That is your answer. Okay. So that is the answer for the entire coil at the center. Now remember that if once we do the electrostatic analysis, then for a charged ring, let us say the positive charge is there, plus Q charge is there. What is the electric field at the point O? Electric field at the center is how much? 0. Okay. So electric field center of the coil or the loop is 0, but magnetic field is not 0. Magnetic field is mu naught I by 2R. Okay. And that number is the maximum number. So B at O is the maximum value of B. Okay, B at O is the maximum value of B. So if I move right hand or left direction towards the point O, okay. So B at the center of the coil is mu naught I by 2R. So if I say the coil has n number of turns, so if I say the coil has n number of turns, so you have to multiply by n. Okay. So B is equals to n into mu naught I by 2R, where n is the total number of turns in the coil. So I can use a single turn coil or multiple turn coil. So once I increase the capital N number, that means B number is going to be increased. Okay. So in some situation, I need more the value of magnetic. So in order to create more value of magnetic field, I can either increase the I number, okay, or I can reduce the smaller number. So smaller is the loop radius. So, or I can increase the capital. So it is better to use a high value of capital N number of turns to increase the magnetic field strength at the center of the coil. Okay. And the magnetic field strength that I am getting at the center of the coil is the maximum. So B at O position is maximum. As I am moving away from this coil towards right hand or left, okay. So if I situated myself over here, so if I curl my finger along the arrow direction of the eye, so magnetic field at this point will be in this direction. This is the B vector. Similarly, if I curl my finger along the same direction, magnetic field on the left hand side also in the same direction. Okay. Left hand side will also be the same direction. So that is not the case for the electrostatic. So if I consider charged ring, so for the charged ring, both right and left side, the direction of electric field is going to be changed. If I say this is a charged ring, a plus Q charge, if I point one particular point over here, A point, so for this A point, the electric field at point A should be positive. Electric field at point A is positive direction. But if I situate myself over B point, so for that, electric field will be negative because a positive charge particle will feel a repulsive force at point B. Similarly, point A will again feel the repulsive force. That means about the center O point, electric field changes its direction. If I say right hand side is positive, then left hand side should be negative. But that is not the case for the magnetic field. So for magnetic field direction is never going to be changed. Okay. If it is positive, then it should be remain positive. If I rotate the current in the other direction, then it becomes negative, but throughout it should be negative. And I have already said that the B value will be maximum over here. Okay, B value will be maximum when R number or X number is equals to 0. That is the center of the loop. And as we move away from the loop, so gradually the number will decrease like this. Okay. So at any position, the magnetic field will be different other than the B value. But on the right hand, left hand side, there are two positions. Let us say this is the one position is X1 position, there is another position X2 position, where the magnetic field line will be same. Magnetic field line will be same. And that is another difference between the electric field. So for the electric field, if I plot the electric field line, so at the center electric field line will be 0. At the center electric field line will be 0. And if I go towards right hand side, it will increase and then again decrease. So for the left hand side, it will decrease and then increase like this. So these are the 2 points where it becomes maximum and minimum. So that number where the E is maximum is basically plus R by root 2. And here it is minus R by root 2. So here the position of the maximum and minimum will be different. Position of maximum and minimum will be different. But here is the center of the coil where the B will be maximum. Okay, B will be maximum. And in this particular situation, there is one point where the positive field will be equal. Positive field will be equal. And there is another set of points where the negative direction field will be equal. But here I can get two different points where the magnetic field remains same on right hand and left hand side of the loop. Okay, so these two numbers are to be remembered. Here the maximum is over here. These maximum at the center position. If I move away from the center, then the magnetic field line is decreased. If I move away from the center in the left hand direction also, then the magnetic field line is going to decrease. Okay, so there is the difference between the magnetic field line and the electric. বোঝা গেছে? হ্যাঁ বলো কোনটা রাইটের দিকে হবে কেমন করে হবে আমি ঘোরাচ্ছি থামটা কোন দিকে ফিঙ্গারটায় ঘোরাচ্ছি কোন দিকে হ্যাঁ তো লেফটের দিকে রাইটের দিকে করেছি তো ঠিকই তো করেছি এই যে অ্যারোটা করেছি অ্যারোটা যদি এই দিক থেকে দেখি তাহলে কোন দিকে দেখবো এখানে অবজারভেবল প্লেস তো এই দিকে ঘুরছে এই দিকে কারেন্ট এই দিকে যাচ্ছে এরকম করে যাচ্ছে তাহলে আমি এটা এবার ছবিটা দেখে তো একটু ডাউট হতেই পারে এইখানে এই ডিরেকশন দেখি কি এটা হচ্ছে ফর দ্য অবজারভার টুয়ার্ডস ফর দ্য অবজারভার যদি দেখি দ্যাট ইজ ইন দ্য অ্যান্টি ক্লকওয়াইজ ওকে এই অবজারভারের জন্য আমি যে ছবিটা এঁকেছি ফর দিস অবজারভার দ্য কারেন্ট ইজ গোয়িং ইন দ্য অ্যান্টি ক্লকওয়াইজ ডিরেকশন তো অ্যান্টি ক্লকওয়াইজ ডিরেকশন লেফট হ্যান্ড রাইট হ্যান্ড সাইড থেকে কার্ল কর ফিঙ্গারটাকে সো থাম উইল বি পয়েন্টেড টুয়ার্ড রাইট বোঝা গেছে আমাকে বলে দেবে আমাকে অঙ্কতে বলা থাকবে কোশ্চেনে বলা থাকবে ইন হুইচ ডিরেকশন কারেন্ট ইজ মুভিং অনলি অ্যারো ইজ নট সাফিসিয়েন্ট অ্যারো দেখে বোঝা মুশকিল হয় ঠিক আছে এই লুকটা কোন প্লেনে আছে কেমন করে আছে এই যদি দেখতাম তাহলে আমি ভাবতাম এই লুকটা কিরকম করে প্লেনে এই প্লেনে লুকটাকে রাখা হবে বুঝতে পারছিস কি হ্যাঁ and the current is going the anti-clockwise direction so curl your finger and in the anti-clockwise direction thumb will be pointed towards right okay so magnetic field is never going to change its direction it is always remaining same okay and important formula regarding this is that v should be equal to mu naught I by 2 capital so when the loop is full so for the half loop it should be mu naught I by 4r for 1/4 loop it should be mu naught I by 8r so for any angle alpha I can calculate that also okay so for the total angle 2 pi for the total angle 2 pi I am getting the value of v should be equal to mu naught I by 2r if I say the loop as having an angle of alpha, that should be equal to mu naught I by 2r into alpha by 2. Okay. Mind you that alpha has to be taken in radian. Okay. So if I say there is one loop which is making an angle 60 degree at the center, which is the part of the loop, which is alpha equals to 60 degree given. Okay, current is flowing in this direction. So you want to calculate the magnetic field at the point O. So your formula should be equal to mu naught I by 2r into alpha. Alpha means pi by 3 divided by 2 pi. Okay. So 1 by 6. That is mu naught I by 12r. Okay, that will be your answer. So for any angle alpha, I can calculate the magnetic field at the point O. Only we can calculate the magnetic field at the center or any angle. I cannot calculate with the knowledge. I cannot calculate what is the magnetic field at this position. So it is somewhat eccentric from the center. So this point magnetic field cannot be calculated with the knowledge that we have. Because that cannot be calculated using the simple Biot-Savart. So for that you have to use some other expressions. So that is not in your scope. So I will omit that part. Only thing is that you can calculate either the magnetic field at the center position of the loop or any axial direction. Okay, or any axial direction. But since it is a vector quantity, you have to also mention the direction in which the magnetic field is there. Whether it is dot or cross. So for this situation, let us say for this diagram, so since the current is being flowing in the anti-clockwise direction, if I place my finger along this direction, the thumb will be pointed outward. The thumb will be pointed outward means I say that whatever the magnetic field that I am getting, it is dot. Okay. So like this way you have to take the direction in which the magnetic field is there and accordingly you have to apply the formula. Okay. So now do this. Let us say there are coil in which the current is being flowing. For the first coil, there is current. There is second wire, then the third wire, then the fourth wire. Okay. So you are asked to calculate the magnetic field at the centermost position. So both 2 and 4 will give zero magnetic. So B at point 2 should be equals to B1 plus B2 plus B3 plus B4. Out of this 4B, so 2 and 4 will be 0. 2 and 4 will be 0. Why? Because 2 and 4 are lying or where, which is lying on the O point. On the O point. So for 2 and 4 it will be 0. But for 3, so if I curl my finger along the 3 direction, so magnetic field will be into the plane of paper. So if I say for the 3 is cross and for the first one it should be dot, because if I curl the finger along the anti-clockwise direction it should be dot. So that means one number is positive, another number is negative. Okay. And this is a half loop situation. So if I say for this loop, for this one first loop, so can I write mu naught I by 2r? Mu naught I by 4r. 4r, because radius is r. And for this loop, it should be mu naught I by 4r. Now the 4r is how much? 2r. 4 times 2r. That means mu naught I by 8r. Okay. So this 8r number is in the cross direction and 4r number is in the dot direction. So B at O point should be equals to mu naught I by 4r minus mu naught I by 8r. Okay. So ultimately your answer will be mu naught I by 8r in the dot direction. Okay. You have to mention the direction also, because whatever you are doing, you are adding this to in vectorial. Once I add this to in vectorial condition, then only I can get the either dot or cross direction. So depending on that, you have to answer it. Okay. So the wire may be a combination of infinite wire also. Again, you are asked to calculate the magnetic field at the point P. So identify how many wires are there. So let us say this is the first wire, then this is the second wire, then this is the third wire. So B at point P due to B1 plus B2 plus B3. Now out of these 3 where 3 will give the 0. Why? Because for the 3 where the 3 where third where is passing through the point P, so it gives 0. So B1 is basically semi-infinite wire. B1 is basically semi-infinite wire. So for that, what is the direction of the magnetic field at point P? Stretch the finger along the, stretch the thumb along the I direction and stretch the fingers toward your point P. So now the magnetic field due to first wire will be crossed. Okay, into the plane of paper. So B1 is crossed. Similarly, if I check for the B2, so finger curled along the 2 direction or the current direction, again the thumb will be pointed inward. So B2 will be again crossed. That means you have to add these two numbers. Now simply use the formula. So for the semi-infinite wire, it should be equal to mu naught I by 4 pi r. Now, for the semi-infinite wire, it should be mu naught I by 4 pi r. And for the half loop, it should be equal to mu naught I by 4r. So both these two numbers will be added up. So ultimately, this will be your answer in the cross direction. Okay, in the cross direction. So the wire may lie in the same plane. So for this particular situation, if I say this is the one plane, inside this plane only all the wires are lying. That means 1, 2, 3, both are lying in the same plane. Let us say this is the XY plane. Okay. So it may not be such that all the wires are lying in the same plane. They may lie in the different plane also. So if they are lying in the different plane, then you have to take it in vector format. Okay. Take it in vector format. So like this way, let us say this long wire carries a steady current. It is bent into a circle of 1 turn. So there is a long wire which carries a steady current, which is bent into a circle of 1 turn, and the magnetic field at the center of the coil is B. It is then bent into a circle loop of n number of turns. The magnetic field at the center of the coil will be how much? Okay. So when the bent in the circle of 1 turn, so then the magnetic field at the center of the coil is B. That means if I say this is the wire of radius, let us say R1. So for this situation at point 2, in the initial situation, B at point 2 is equals to mu naught I by 2R1. This is the first situation. Now we bent in n number of turns. Okay, bent in n number of turns. Let us say the n number of turns are there. So for this situation, let us say R2 is the loop radius. R2 is the loop radius. So B at O point for the second situation, let us say prime, it should be equal to mu naught I is same current. It is 2 into R2, but you should multiply it by n number. Okay. Now you have to draw the relation between R1 and R2. So initially the loop wire length is L. Wire length is L. So for that situation, if I say L should be equal to then 2 pi R1, and here L should be equal to 2 pi R2 into N. Now both are equal. So can I say R1 should be equal to R2 into N? The relation between R1 and R2. So once I find the relation between R1 and R2, so this can be written as mu naught I by 2R. 2R2 means 2 times of R1 by N multiplied by N. So ultimately what I am getting? Mu naught I by 2R1 multiplied by N square. Okay. Now this number is how much? This number is basically our B number that is given initially. So final B should be equal to how much? B into N square. Okay. So option number 2 will be the correct answer. So once we increase the number of turns, once I increase the number of turns, then what is happening? Then that means R radius is decreasing. So initially the formula is B should be equal to mu naught I by 2R. This is the formula. So once I increase the number of turns, so then N will come in the numerator. So N will increase. And with the increasing number of turns, the radius of the coil is also decreasing. So R is in the denominator, so it is decreasing, means overall B will increase. So how many fold? It will increase by N squared time. N squared time initial B value. Okay, provided I am keeping the same amount of current. In both the situation, I am supplying the same amount of current. So your answer should be equal to N square into B. Okay. So like you said, these are the some simple problems. You can do it. Now come to the this problem. Yes. So now the angle is given as theta. Now the angle is given as theta. So I have to use the general formula. So for where 1, then 2, then 3, then 4. So along the 3, the current will be flowing in this direction. Now again, B at point 2 is only contributed due to first wire and third. 2 and 4 will no contribution because these two wires are passing to the point O. So B at point 2 is due to B1 and B2. Now check the sign. So for the B1, it should be dot. For the B1, it should be dot. And for B2, it should be cross. That means in between, it should be minus sign. If I take dot is positive, B2 should be negative. So ultimately, your answer will be minus 1. Now, general formula for B, for any angle alpha is equal to how much? Mu naught I by 2R into alpha by 2 pi. That is the angle. Okay. That is the number. So here alpha is theta. So B1 should be how much? Mu naught I by 2R. Capital R is R. Okay. And alpha is theta by 2 pi. Theta by 2 pi. Minus B2 mu naught I by 2R. Now the R is 2R. So it becomes 4R. 4R into again alpha is same. For the third wire and the first wire, both the alpha values are same. So it should be again theta by 4 pi. Okay, theta by 4 pi. So ultimately I can simplify it as mu naught I by 2R into theta by 2 pi if I take common. So ultimately I am left with 1 minus 1 by 2 into 1 by 2. Okay. So ultimately, so theta by not 4 pi here also theta by 2 pi. Theta by 2 pi. So only change is not half will be there, only 1 half will be. So 1 minus half is half. So ultimately I am getting 8. 8 pi here. So your answer is equals to mu naught I theta by 8 pi. That will be your answer. That is option number 8. Okay. So if the wire is of any angle, then you should go for this formula. And if the wire is either half or 1/4, then you directly the formula like that. Okay. So like this way, there are some problems. So this is another type of problem. Same problem, only thing the values are given, so you have to calculate it. Okay. So I am not doing, these are, let us say, for your homework part, these are the same problem. Okay. Now, coming on to this situation. If the intensity of the magnetic field at a point P or axis point P of a current carrying coil is half that of the center of the coil, in the distance of that point from the center of the coil. So here, let us say this is the P point, and the O point. So question says that the magnetic field at point P is equals to E at point O by 2. Now, what is the magnetic field at point P? The formula is mu naught I into R, mu naught I into R square. Yeah, mu naught I into R square. R is the capital R is the loop radius. Mu naught I by R square in divided by 2 times of R square plus X square whole to the power 3 by 2. That number is B at point P, and that should be equals to V naught is mu naught I by 2R whole divided by 2. Okay, so to simplify it, so ultimately what I am getting that mu naught I cancels out. So in the numerator R square is there, and these two cancels out. So R square divided by R square plus X square whole to the power 3 by 2. That should be equals to mu naught I cancels out, 2 cancels out, so 1 by 2R. 1 by 2R. Okay. So ultimately we are getting 2R cube equals to R square plus X square whole to the power 3 by 2. Okay. Now you have to square both sides. One side square the both sides. What I am getting? 8R to the power 6 should be equals to R square plus X square whole to the power 3. That means R to the power 6 plus X to the power 6. Huh? You only use the runner. 4 R to the power 6 হবে কেন আমি তো আচ্ছা স্কোয়ার করেছি না স্কোয়ার করে রাইট it should be 4 R to the power 6 4 R to the power 6 that should be equal to R to the power 6 plus X to the power 6 plus 3 times of R square X square into R square plus X square 3AB into A plus B. So ultimately I can solve to calculate the X. So 3R to the power 6 should be equals to how much? X to the power 6 plus 3R to the power 4 X square plus 3R square X to the power 4. So that becomes a quadratic of X. That becomes a quadratic of X, and ultimately you have to solve. So once you solve it, so your answer should come as option number D. That will be your answer. Okay. You have to simplify it and calculate. Okay, these are the 2 points where I can calculate the magnetic field at point P and similarly magnetic field at point O and use the relation to calculate the distance X. Okay. Now moving on to the same next segment. Now we want to check about the field lines. How the field lines are looking and what are the field lines for the solenoid. Because I am completing 2 geometry. One is the wire, another is the loop. Now moving to the solenoid geometry. So these are the 3 important segments of the magnetic field calculation. And apart from that, there is another geometry is there, that is the toroid geometry. So coming to the solenoid geometry. So first we are understand the property of the magnetic field. So to visualize the magnetic field line graphically, Faraday introduced the concept of magnetic lines of force. Now here, the field, in case of electrostatic, whatever the electric field line, those are the same as the electric lines of force. Why? Because if I say there is a positive charge, from where that this is the electric field line coming. Okay. So if I say that is the electric field line, if I place one charge over here, so that will feel the same force along the electric field line. So force vector should be also along the electric field line, either parallel or anti-parallel, depending on the nature of the charge. If I put one negative charge over here, so then this charge will feel a force in the opposite direction. Okay, but it is anti-parallel. So once I draw the electric field line, that means I can also predict the electric lines of force. But that is not the case for the magnetic field line. So here the magnetic field lines are magnetic field lines and magnetic lines of force are two different. Why? Because whenever we study a wasted experiment, then you see that if I place a current carrying wire and through the current is going in this direction, so I know that if you consider this particular point, so at this point A, magnetic field line will be dot. Magnetic field line will be dot. So here the magnetic field line will be dot. At each and every point, the magnetic field line is dot. At each and every point on the right hand side of the current carrying wire. But once I place a charge at this point, I see that if I throw the charge in this direction, the charge will bend in this direction. That means This particular direction will give the direction in which the particle has been displaced or direction of deflection. But once I say the deflection is there, that means at this each and every point, the particle velocity is constant. The velocity is not going to be changed. So since the velocity is not going to be changed, that means there is one force is acting which is creating the deflection, and that force must be perpendicular to this. That force must be perpendicular to this. So this is the direction of the magnetic force at this particular point. But at this point, if I see the magnetic field should be dot again. Okay, that means magnetic field lines direction and the force direction are not same. Rather, they are perpendicular to each other. So that means magnetic field lines cannot be treated as the magnetic lines of force. Okay, so initially I draw the magnetic field lines. Once I draw the magnetic field line, then based on that magnetic field line at that particular point, I can analyze what is the direction of the force. Okay, so force vector and field vector are perpendicular to each other every time. That means these two terms are different here, but these two terms are same in case of electrostatics. In electrostatics, if I see electric field lines, so that is nothing but the electric lines, but that is not the case in case of magnetic. So if I want to plot this direction, in which direction the arrows are bending, that means I know that from north pole the magnetic field lines are coming and they are ending on the south pole, but it is outside the bar. Outside the bar magnet. Inside the bar magnet, they must be closed lines. So these must be the magnetic field line from south pole to north. Inside the bar magnet, it should be always south pole to north pole, so that all the field lines are closed in it. And if I place a magnetic needle or magnetic compass, so compass will always show the deflection along the direction of the magnetic. By measuring the deflection of the compass or magnetic needle, I can plot the magnetic field. Okay, so it cannot be visible. I cannot view it. But once I place the magnetic compass, then I can see in which direction the compass is moving. Accordingly, I can judge what is the direction of the magnetic field lines. Okay. So these are the imaginary lines. So these are the imaginary field lines which represent the direction of magnetic field continuously. Okay. So these are the different geometry that we have already learned. So current carrying wire, loop, all are known. Only thing the solenoid is not known to us right now. Bar magnet is also known to us. And regarding the arc magnetism, we will discuss about this in the later part of the course. Initially, we have bothered about the current. So once I supply a current, so how the magnetic field line being created? So I can supply the current through a wire or through a loop or through a solenoid, and for all those geometry, the field lines are being created. Okay. So tangent drawn at any point on the field line represents the direction of the field at that time. So this is the same property that you got for the electric field lines also. Okay. So if I look at one particular point over here, if I draw the tangent at this point, so that a B vector should be directed along this direction. So for this point, tangent is like this direction. So these are the direction of the magnetic field lines at different points, and they are continuously changing. They are continuously changing. So magnetic field lines are always closed curve. Magnetic field lines are always closed curve. That means this is the deviation from the electric field. So far, what about the electric field line that we learned? Those electric field lines can never exist in a closed. But in the later part of this magnetism chapter, once we deal about the electromagnetic induction, then you see another type of electric field lines. That's called the induced electric field line. So those induced electric field line will always exist in a closed curve. Okay. But whatever the electric field line that we have learned so far, those are the due to the charge. So whenever the charge is there, because we are charged, electric field lines are coming into the picture. So those electric field lines that are developed due to the point charge or any distributed charge can never exist in a closed. But whenever I am discussing about the magnetic field line, so these magnetic field lines are always closed. They are not open. They are not open. So field lines will never intersect with each other. That is also true for the electric field lines. So this is the second property of the field line, where I can say if I say these two field lines are intersecting at this particular point. So let us say the first line, is the second line. So if I draw the tangent at point number 1 for the field line 1, so that should be the direction of B at this point for the first field line. So similarly, if I draw the tangent at point 2, then it should be 2. So these two are the different field lines measuring at the same point A. But I know that at point A there is only one and only one direction of magnetic. Okay, this is the same logic for the electric field lines also. Electric field line cannot intersect, magnetic field lines also cannot intersect with each other. Okay, so magnetic field line may be uniform or may not be uniform. Magnetic field line may be uniform, may not be uniform. So what is the meaning of uniform? Means constant. So same is the logic for the electric field lines also. So we have said that electric field line may be constant in uniform electric field line or may not be. So for a simple infinite charge sheet, so we can say the electric field lines are constant, that is equal to sigma by 2 epsilon F. But for any other geometry, like current, like a charge wire or charge rule, so for those situations, the electric field lines are variable. Here also the same situation. If the magnetic field lines are uniform, then these lines are equidistant and straight. That means the gap between these two lines. So this is, if I say this is a B naught value, this is also B naught value. All are B naught. Magnitude should be same, and the gap should be represented by same. So whatever the direction D is there, gap between the two field lines I am plotting. If I plot the gap to be equal, then only I can ensure that I am plotting a correct representation of the uniform field line. Similarly, these two gaps, whether this gap or that gap, should be equal. Okay. So if these gaps are equal, then it's called uniform magnetic field. And if it is non-uniform, then gap must be different. So if I say gaps are different, gaps are different. So here you can observe the gaps are small. Here I am putting the gaps are larger. That means I can ensure that the magnetic field lines are not constant. Why? Because for a current carrying wire, I know that magnetic field line B should be equal to mu naught I by 2 pi r. Okay. So as I am moving away from the wire, so magnetic field lines are decreasing. Field strength are decreasing. It is only maximum at the on the line itself, but you cannot define the value of that magnetic. That is also important point, is that by moving the value or increasing the value of R, I can ensure that as I am moving away from the R, so R is increasing, so B is decreasing. And once I reach the infinite value, so I can say that B is tending to 0. But once I am moving toward the wire, gradually the B value will increase. So B value is increasing means the separation is increasing. Yeah, separation is decreasing. So if I put myself on the wire, if I say O is a point which is on the wire, so for point 2, I cannot define B. B at point 2 is not defined. Okay, because at this point, if I put R equals to 0, so B is infinite. At R equals to 0, B is infinite. So that means I cannot define the magnetic field around the wire, on the wire itself. So crowded lines, once the density of the lines are more, so here the density lines is more. So these are representing crowded lines. So represent a stronger field. Stronger field. So when the distant lines are there, it represent the weaker field. So more the crowding, more is the magnetic field density. Less the crowding, less is the field density. Okay. So magnetic field lines, I have already said that these lines can only be traced by using the iron lines. So I can trace it. I cannot see it actually. In order to view it, you have to trace this diagram. So once I trace the diagram by doing some kind of experiment, then only I can see what is the magnetic field, how it looks. And I can ensure once I trace these lines must be close to one again. Okay. So these are the different representation of the magnetic field lines. So they are mapped by using iron. So here the magnetic field lines are plotted for the 2 bar magnet. So this is the bar magnet number 1, this is the bar magnet number 2, and this is called the keeper. This is called the keeper, which is holding these 2 bar. Holding these 2 bar magnet. So if I plot this, so by seeing these lines, I can estimate that here if I say this is the north pole, so it must be south. Why? Because magnetic field lines are coming from the north pole, must enter in the south. If I say this is south pole and this must be the north pole, if I say magnetic field lines are coming from the north pole, it should terminate on the south pole. Okay. So if I say both are north pole placing together, so they will not intersect. One field line from north pole cannot interact with the another field line in the north pole. They will never interact. Okay. Only the similar is the logic for the charge also. If I say this is one positive charge, this is one negative charge. So electric field line emitting from the positive charge should terminate on the negative. Okay. So same logic, if I say replacing the, every time I will put the analogy like this way that positive charge is basically the corresponding to north. Okay. So negative charge behavior is similar to the south pole. The same logic, if the magnetic field lines are coming from the north pole, they will enter inside the south. Okay. So they can only enter if the poles are different. If the poles are same, they cannot interact. Okay. So this is how you have to place your compass along the bar magnet so that I can place it. Okay. If I place our compass over here, so compass will be pointed toward the north. So why? Because from the north pole magnetic field lines are coming. So here also the compass will be like this. Okay. If I rotate this compass, let us say I am placing over here. So here the magnetic field lines is somewhat inclined, let us say. So this is the direction of the compass. Like this way the compass will reflect, and once I measure this deflection by putting dot points on a piece of paper, I can estimate about the magnetic field direction. Okay. So always circular loops are there once I allow the current to flow on a current carrying wire. So these are the circular loops that we generated on a piece of paper. If I allow the current to flow in this direction, so then the circular loop will be generated, and these lines are concentric circles. And once I plot this line, I have to ensure that since the magnetic field line is a variable field line over here, it is not a constant. So the gap between these two lines will gradually increase. So if you draw this diagram, so you have to ensure that this gap, so let us say this is the R1 number, first one, then R2, gap is R3, gap is R4, like this way. So R1 is less than R2, R2, like this. So gradually, as you move away from the center of the wire, so the distance between the magnetic field lines should increase. Okay. Now, on each and every point, on a particular loop. So let us say I am saying this is the loop. So on this loop, on each and every point, the magnetic field line should be same. Yeah, magnetic field line, magnitude wise should be same. Direction is different. Magnitude and magnetic field line is the same, but the direction will be different because it is always changing direction. Okay. When the current is circular means along a loop, the field line is straight only along the axis. If I say this is the direction of current, and I am saying this is the direction of the magnetic field line, and that direction is only for the center. That is the line which is passing to the center, that means along axis. I cannot comment that all the field lines are straight. Only one single line is straight one, all the other field lines will be curved. All the other field lines will be curved down. Similarly, when the wire is placed in a piece of paper, on a plane of paper, the field line is perpendicular to the plane of paper. And it is always distributing the field line in two different segments. If I say that part is the cross part, that left part should be the dot. So it will always distribute to two different segments on the right hand part and the left hand part. And that is the same logic for the loop also. If I say this is the loop, so 2 is, let us say, this is the current direction. So inside the loop, the magnetic field line will cross. But outside this, it is always there. Okay. So every time a current carrying element is placed, and if we allow the current to pass through that element, then it will distribute the magnetic field into two different segments. One part of the segment will be cross magnetic field, another part of the segment will be having dot magnetic field. It is always true that it will form. So when wire is perpendicular, so if I say dot magnetic field is there, so I can say this is the direction of magnetic field. The cross current is flowing. So this is the direction of the current. So here the cross is the direction of current. So place your thumb along the cross direction or dot direction and curl your finger. So the curling direction will be the direction of the behavior. Okay. So like this you have to plot it. So for the permanent magnet, for the bar magnet, one important point is that the field lines will start from the north pole and will end on the south, outside. And inside the bar magnet, the field line should from south to north, so that it will make a closed path. Okay. So on a piece of paper, I can show some lines. So if I say this line, and correspond to that line is there. So ultimately these two lines will meet at some point. Okay, I cannot show in a limited space, but it is actually happening that after going some direction, comes again back to the south pole. That means the number of field line that is coming from the north pole should meet on the south pole. All the lines should be closed one. All the lines will be closed one. So now come to the solenoid. So far we understand about the magnetic field property, magnetic field line property, and we say these properties are more or less similar to the electric field line, only difference in some situation, and you have to remember the difference between the electric field line and the magnetic. How it differs, when it differs, and why it differs. Now come to solenoid. The solenoid is basically a spiral type of geometry. Solenoid is basically a spiral type of geometry. And again, first of all, I have to understand what is the direction of the magnetic field. So in order to calculate the direction of the magnetic field for the solenoid geometry, again, you have to curl your finger along the I direction, along the direction of the current. So once I see the current is being flowing in this direction, let us say current is being flowing along this direction. If I fold my finger along that particular direction, so then B will be pointed like this. So once I get the direction of the B, so now I can replace this solenoid by again a bar magnet by saying this is behaving as a north pole, this is behaving as a south pole. Okay, why north pole? Because from this I am saying this is the magnetic field that are coming out. Okay, so whatever the field line that is coming out from the solenoid is basically direction is along the north. So this is behaving as a permanent magnet, though it is not. But in some situation I have to analyze it. So for that it will be easier if I replace the entire geometry by a magnet. So for replacement of the magnet, replacement of the geometry to a magnet, every time I have to use this kind of analogy. Okay. So now this is the kind of solenoid. So I know what is the direction. Now, so for the direction again, you have to take the right hand thumb rule. You have to curl your finger along the direction of the current. And once I curl my finger along the direction of the current, so let us say this is the direction in which I am curling this. So current is flowing along that direction. Okay. So thumb will be directed toward the magnetic field. So here magnetic field will be vertically upward like this. This is the magnetic field direction. And I can ensure that once I place a magnetic compass over here, the north pole will be pointed upward. Similarly for this, since the magnetic field line is going in, so north pole should be over here. Okay, pointed toward the magnetic field line. So this is how I can plot the magnetic field line for the solenoid also. Okay. So if the current is changing in direction, so now the magnetic field line is going downward. So this part downward means down toward the arrow, the north pole should be there. Here the north pole is downward. So arrow is downward means north pole is downward. So it should be the south pole facing this, and it should be north facing that direction. So like this way I can replace the solenoid by a permanent magnet. Now regarding the solenoid, the solenoid basically is made up of wire. First of all I have to put a conducting wire which is wound in a closely spaced wire. Closely spaced means the gap between these. So if I say this is the first wire, this is the second wire. So gap between these two wires should be very minuscule. Okay. So in a spiral over a hollow non-conducting cylindrical core. So there is a non-conducting cylindrical core about which you have to wound it so that you can make a solenoid. Okay. Now, what is small n? Small n is called the number of turns per unit. Let us say I am saying for this particular geometry, capital A is the number of turns. And I want to calculate the length L number. So what is L? L is called the linear dimension. Linear dimension for the length of the solenoid. So now small n is basically capital N by L. But mind it that L should be kept in meter, not in centimeter. So once I kept L in meter unit and divide it by N, so then it gives the value of small n. So linear dimension must be greater than the transverse dimension. So what is transverse dimension? So transverse dimension is basically, so linear dimension must be much greater than the transverse. The transverse dimension is nothing but the measurement of the radius of the solenoid. Let us say this is a smaller number. Okay. So transverse dimension is the radius of the solenoid and linear dimension is length of the solenoid. Generally, most generally, R is measured in millimeter unit and L is measured in centimeter unit. Okay, if I say small r is around say 2 millimeter and L is around let us say 10 centimeter. So can I say that 2 millimeter is much greater than the 100 millimeter? So 2 millimeter is much greater than 100 millimeter. So 2 millimeter is much less than the 100 millimeter. So that means this dimension is correct. And if that is correct, if that is this statement is correct, then this solenoid is known as the ideal solenoid. Okay. So for ideal solenoid, linear dimension must be greater than the transverse dimension. That means all the solenoids are not ideal. If it is ideal, then it's true. If it is not ideal, that means there is a mismatch in this number. So when I say R is more or less comparable in dimension L, so then I say it is a non-ideal, and for non-ideal, the analysis will be different. Okay. So first of all, I have to understand that this is an insulated long wire wounded over a cylindrical in the form of a helix, collection of circular loops touching each other. So there is very bare minimum gap. I am saying that the gap between these two wires is very, very small. That means all wires are touching. All the wires are touching. Okay. If I allow the current to flow in this direction, let us say I am allowing the current to pass through. So through this loop, the current is going in this direction. Through this loop, current is going in this direction. And from the uppermost point, can I say current is moving in this direction? So both the direction of current in this point is towards the into the plane of paper, and here it is coming out from the plane of paper. Okay. So for all the upper point, if I draw all the upper point, this point, that point, this point, all the upper point coming, current is moving out of the plane. And these are basically represented by dot. Okay. And these are the point in from which the current is going inside the plane. So these can be represented by cross. Okay. So once I cut this solenoid, if I cut this solenoid with a vertical plane, if I cut this solenoid with a vertical plane, so what I am saying, so these are the tip of the wire. In between there is no hollow part. So in between there is no part. So upper part is dot 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 like this. Okay. Lower part is cross 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 like this. So this is the cross section of the solenoid that I want to see. Okay. And the gap between these two cross is very, very small. Gap between these two cross is very, very small. So either I can say the lower part is cross or upper part is cross. These two directions must be different to each other because current is going into the plane of paper, then moving out of the plane. So that means these two directions must be opposite to each other. They cannot be same. Shape of the solenoid can be circular, can be rectangular depending. What is the shape? Shape is this cross section. The cross section can be of any geometry. It may be circular, it may be rectangular. But in our syllabus, only circular coil is there because I have already calculated the circular coil. Okay. I have to generalize that. I have already calculated the magnetic field strength due to the circular coil, circular loop. Okay. Now I want to generalize that for the solenoid. The solenoid is basically a collection of n number of circular loops. Okay. So if I say here the number of turns is n, so basically it is nothing but n number of circular loops. Circular loops. And these circular loops are placed very close to each other. Very close to each other. So earlier I have calculated one loop. Now I have to calculate the same situation for n number of loops, but in a different way. Okay. So this is the geometry that we want to follow. So this is the cross section of the solenoid. I want to calculate the magnetic field line due to solenoid inside the solenoid. Inside the solenoid. So let us say there is a point P. From point P, at point P, I want to calculate what is the magnetic field at point P. B at point P, I want to calculate. So for that, I take a section of element like this. So I take a section of element like this way. So this particular section is nothing but a multiple closed coil. So if I see, this is basically the section where can I say this is the, if I say this particular situation, this particular section is nothing but a coil like this way. Okay. So for this section, point P is located, let us say point P is located at a distance of x from the center of this loop. Okay. So this is the cross section of the solenoid. Entire section of the cross section of solenoid is drawn. I want to calculate the magnetic field strength due to the solenoid at point P. So for that, what I am doing, I am taking a point P which is at a distance of x from the section. So this is the element that I have taken. In the current element I have taken that from. So what is this element? This element is a circular coil. And circular coil of some turns. Number of turns must be there. Okay. Let us say I am saying this number is this thickness of this circular coil is, let us say dx. Dx. So dx is the thickness of the circular coil. So By moving a distance of x, I am taking a dx element. So inside this dx element, not a single loop is there, n number of loops are there. So what are the number of loops? If I say small n is the number of loops, small n is what? Number of loops or number of turns per unit length. Okay, per unit length. So in this particular section of coil, can I say the number of turns should be equals to a into dx, small n into dx, because dx is the length of the loop, length of the element. Within that dx length, how many wires are there? How many loops are there? That is n multiplied by small n multiplied by dx. Okay. Now the situation like this way. So there is a coil of turn dn, that is equals to n into dx. And now from the center of the coil, now we want to calculate the magnetic field distance of x at point P. So I can apply the formula for the loop. I have already calculated the loop formula. So that is equals to mu naught I into capital R square divided by R square plus x square whole to the power 3 by 2. This formula I have to apply with capital N multiple. Okay. So this is the formula that I am going to apply for calculation of the solenoid. Okay. Now, what is the value of mu naught? Mu naught is same. So I want to calculate the dV. So dV should be equal to mu naught I. What is I? I is the same amount of current that is going through each and everything. Okay. I in the same amount of current. So mu naught into I into capital R square. So capital R is what? Capital R is this number. This number is capital R. Remain capital R square divided by capital R square plus x square. Capital R square plus x square into 2 times. So 2 is. So 2 times of R square plus x square. R square plus x square into whole to the power 3 by 2 into n. N is how much? A into dx. So this is the equation that you have to solve it or integrate to calculate the B number. Understood? So for that I have to eliminate. I have to substitute, because there is a function x that comes in the denominator, and in the numerator there is one dx is there. If I say tan theta, if I say at any situation, let us say I am saying this is the section of the loop which is making angle theta. So theta is the angle made by the loop at any particular section. So tan theta, let us say this is the not theta 2, let us say angle theta. So tan theta should be equal to how much? Then capital R by x. Okay, the element I have taken which is making angle theta at the P point, which is tan theta equal to R by x. So can I say x equals to capital R tan theta? The capital R tan theta, capital R cot theta. No, capital R cot theta. X equals to capital R cot theta. So x equals to capital R cot. Now I have to calculate the dx number, because in the numerator dx is there. So dx equals to how much? Dx equals to minus R cosec square theta d theta. Cosec square theta d theta. So this is the dx. So if I put x equals to R cot theta, so in the denominator it will become R square plus R square cot square theta. So 1 plus cot square theta is cosec square theta. Okay, 1 plus cot square theta is cosec square theta. So finally I can say that dV that I am getting, that is equal to mu naught into I into capital R square into small n into what is dx? Dx equals to minus R cosec square theta d theta. And the denominator gives 2 times of R cube into 1 plus cot square theta whole to the power 3 by 2. 1 plus cot square theta is cosec square theta. So 1 cosec square theta whole to the power 3 by 2 means cosec cube. So 1 cosec square will cancel out, so ultimately we have left with 1 by cosec theta, that is sine. So if I rearrange it, so I am getting that mu minus, or minus sign is there, mu naught into small n into I, and R square R cube cancels out, so I am left with, so whole R cube cancels out, because R is there, R square is there, mu naught R cube is there, so mu naught Ni by 2. Mu naught Ni by 2 into 1 by cosec means sin theta d theta integration. So that will give the value of B at point P. Okay, B at point P. So in order to take the limit, so I want to say This is the one extreme end of the coil and there is another extreme end. Okay. One extreme end is making angle theta 1 from the positive x-axis and another extreme end is making angle theta 2. Okay. Another extreme end is making angle theta 2. So limit should be how much? Limit should be equal to from theta 1 to theta 2. Yeah, theta 1 to theta 2. Theta 1 to theta 2. If I solve this, so integral of sine theta is minus cos. Integral of sine theta is minus cos theta. So minus will cancel out. Ultimately, I am left with cos theta to minus cos theta. I am doing it once again. So b I am getting is equals to integration of db, that is equals to minus mu naught into small a into I by 2 integration of sine theta d theta. The limit is from theta 1 to theta 2. So integration of sine theta is minus cos theta. So minus will be adjusted. So mu naught into ni by 2 into integration cos theta. Limit is from theta 1 to theta 2. Okay. So once I put it, you give mu naught ni by 2 cos theta 2 minus cos theta. So that is the final answer. And that equation or the magnetic field value is independent of whether I am taking for the ideal solenoid or not. So this is the basic equation from where I have to simplify further. So this will give the magnetic field strength for any type of solenoid, whether it is ideal one or non-ideal one, inside the solenoid at point B at point P. Okay. Now what about the ideal and non-ideal? So if I say it is an ideal solenoid, if I say it is an ideal solenoid, then what I am saying that for ideal solenoid, the R number, capital R number is much lesser than the transverse linear dimension. If I say AL is much greater than the R number, then can I say this angle is very small also? Okay, so theta 1 is almost making an angle 180 degree because theta 2 becomes almost 0. Because if I say there is a solenoid whose radius is, let us say, 2 millimeter. This distance is 2 millimeter. Okay, and this distance is, let us say, 100 millimeter. Okay, if I take one point inside, so from this point, if I draw these two lines, so this angle becomes very small. Why? Because this number is 2 millimeter, and if I say this number is 90 millimeter, so 2 by 90 is very small. Then the theta 2 is almost tending to 0, and corresponding theta 1 is almost tending to 180. If I put theta 1 is 180 degree, so cos of 180 is minus 1, and theta 2 is 0, means cos 0 is 1. So 1 minus 1 means 1 plus 1 is 2. So ultimately, we are getting mu naught ni by 2 divided by cos theta 2 is 1 minus of minus 2. That is 2. So ultimately, mu naught ni only. And that B is the magnetic field inside the solenoid for the ideal. So case 1 is the ideal situation. So I want to calculate the whatever the magnetic field at the center position, C point of the loop is same as the any other point, because the C point is any point within the solenoid, and each and every point magnetic field will remain constant. Only thing is that at the edge point. If I come to the edge point, at the end point, if I place my point P over here, so now the theta 1 becomes 90 degree. Theta 1 becomes 90 degree, theta 2 is tending to 0. Okay. So as I move inside this, so ultimately what happens? Theta 1 becomes 180 and theta 2 becomes 0. That is the case number 1. So for the end point, theta 1 should be equal to 90 and theta 2 is almost equal to 0 degree. We have proved it. So theta 1 is 90 degree, so cos 90 is 0. Theta 2 is 0, means 1. So ultimately mu naught ni by 2. And that is again for the end point. This is again for the end point. So what we conclude finally is that if the point is just inside, then at each and every point, magnetic field is constant. If the point is just inside the solenoid, then the magnetic field is constant. If I say the point is lying at the center or any other point, magnetic field line is always mu naught ni by. But at the edge point, magnetic field is mu naught ni by. আগে বন্ধ কর। অডিওটা মিউট কর। At the end point, it is equal to mu naught Ni by 2, and at the center, it is equals to mu naught into Ni. That means magnetic field is more or less constant inside. Only there is slight variation at the center. Yeah. At center, it is mu naught Ni. At the end, it is equals to mu naught Ni by 2, and this for the ideal solenoid. For non-ideal solenoid, there is a slight variation. Okay. So plotting is somewhat different. For ideal solenoid, if I say at the end point, the value is equals to mu naught Ni by 2. And it is small region is there. Between these, there is a variation. After that, once I look at the point just inside the magnetic field, inside the solenoid, the magnetic field becomes constant. That is equals to mu naught into Ni. Okay. So there is small variation of magnetic field at the edge. But that is not the case for the real solenoid. In real solenoid, the variation is much more prolonged. Okay. So I can clearly see that inside the point, if the point is inside, the magnetic field is not equal to mu naught N. At the end point, it is again mu naught Ni by 2. But at the center, it is again mu naught Ni. These are true. But throughout, there is a variation. And this variation makes it real solenoid. And for real solenoid, what you say? Small r is almost equals to L number. Radius of the solenoid is almost in comparison with the length of the solenoid. But for the ideal solenoid, r is much less than the A. Okay. So these are the two different variation of the magnetic field line depending on the whether the solenoid is ideal one or the real one.